All right, so guys, we're going to begin today by posing a question. So if you go with me to chapter 8. So guys, the question that I have is, as we start into this next unit, is why did I choose to have you use the KWL format for chapter 8? And guys, understand, before you answer the question, first of all, one, it's not rhetorical. But guys, number two, let's make sure we understand why we're doing these chapter summaries in the first place. So guys, you get to college and you quickly find out that you don't actually learn from your professors. Many of them resent teaching freshman classes because it's not what they get paid to do. They get paid to research and work with graduate students, and they frankly find you annoying. And so, guys, a lot of times the people that are teaching freshman classes are simply people that can't get out of it. And many times if they can get out of it, what they do is they actually pay their graduate assistants to teach your classes, which then means that many of these fine young lads barely speak English. And so all of a sudden you're going, oh snap, I'm not learning from my professors. So guys, who do you then learn from? TAs, books, and each other. And so guys, understand that in this class, we use this textbook as a supplement, as a resource. But guys, the reason that we're doing this carefully is because soon this is going to become your lifeline. Now guys, understand there are some university professors that actually are also good instructors, but it's not the rule. It's not quite the exception, but it's not the rule. So, guys, with that said, why did I choose KWL for Chapter 8? Because, guys, very soon you're going to be choosing your own outline strategies, and you've got to be able to justify your choice. So why KWL? Go ahead. You knew a lot of it, right, guys? As you page through Chapter 8, you're like, oh wait, Lewis dot diagrams, done that. Ionic bonding, done that. Oh wait, lattice formation, not done that. So maybe that went in the learned or then the manipulative middle column, which is want to learn, which means I still don't understand it. But guys, literally that's what you're doing with this chapter is you're going, wait, I already knew that, or wait, I learned that. I guess I'm backwards to you. Wait, I knew that. Wait, I learned that from reading it, and then everything in the middle is the stuff you couldn't figure out from the text, and that becomes what you want to learn. And then as you continue back, we're back into like page 297. We're looking at Lewis dot molecular structures, single, double, triple bonds, electronegativity, polar molecules, drawing Lewis dot structures. Oh, but then we get to formal charge. What's that? Don't know. Maybe you learned it, maybe you didn't. Depends on where you put it. Then, guys, we keep continuing back from there. We're on page 311. Now we're talking about resonance, which is something we didn't do last year. Did it go in the learned or the want to know column? Because it's not something you already knew. Then we get into these exceptions to the octet rule. Again, something we didn't learn last year. Then we talk about on page 315, strengths of covalent bonds. 317, look, energy diagrams. Oh, we're going to do a lot of those. Then continuing back from there, we ran out of chapter. So guys, that's the thinking behind having you KWL this. You knew a lot of this material, but there were certainly things that you didn't know as well that you either learned from reading it or we get to talk about together. So that was the strategy there. So now guys, do this. Go back to chapter 8. Yeah. Or 7, sorry. 7. My bad. Chapter 7. Back to where you already were. So guys, chapter 7, read the title. Why did we skip chapter 7? It starts on page 249. Guys, reading the title of chapter, don't even page through the chapter, just read the title. Why did we skip it? We did it all last year. So, guys, you don't need to page through the chapter, but what you'll find is you go through, not now, but thinking what's in chapter 7. And it's all about periodic trends. As you go down a group and across a period, what happens to the atomic number? What happens to the atomic mass? What happens to the atomic radius? What happens to electronegativity? And what happens to ionization energy, which is all stuff that we learned last year. So there was no reason to go through chapter 7 because you know all this stuff. But you're going, wait, I don't know all this stuff. Guess what we're going to do right now? We're going to review all this stuff. So, guys, my suggestion to you would be this. What you're going to want to do is, in your notes, skip down. Nah, you don't even need to skip down. But leave yourself some space to the left. Leave yourself some space below. And draw yourself a periodic table. And then, guys, we're going to go over all of the periodic trends that you need to know as we go down a group and across a period. So, guys, let's draw ourselves 5 arrows. Remember doing this last year? Don't lie. Oh, I'm going to run out of space. No, actually, I know. No. Although there was a lot of overlap in what we were doing, but not anymore. All right, so then, guys, we are going to do Z, we're going to do A, we're going to do atomic radius, we're going to do electronegativity, and we're going to do ionization energy. So Z and A and atomic radius and electronegativity and ionization energy. So, guys, my guess is that you can do this, or you probably can do this without even looking at a periodic table. But if you need one, you certainly can grab one or flip to the inside cover of your book or look at the wall or whatever you want to do. But, guys, the idea then becomes this. As we go down a group, what happens to the atomic number Z? They get bigger, right? So I'm going to do this with plus signs and minus signs where maybe I won't. That'll confuse you. So guys, let's just do this. The big numbers are down here and the small numbers are up here. And obviously that means as you go down, there's more protons in the nucleus of the atom. Then guys, moving from left to right, what happens to the atomic number? Obviously it increases. So the small numbers are here and the big numbers are over here. And therefore, the biggest atomic numbers are in the bottom right, and the smallest atomic numbers are top left. Is that good? Okay. Then, guys, the atomic mass, these are the same. This goes small to big, and small to big. And so the big fatties are, well, the small fatties are in the bottom, well, the sort of bigger, smaller fatties are down in the heavy ones are in the bottom right. You guys good there? Okay, now guys, we got to start thinking about these. These are the ones that are more tricky, but I think you're going to have an aha moment in just a minute. But let's talk about the trend first. So guys, atomic radius, which is the distance from the nucleus to the valence electron shell, as you go down a group, does the radius get bigger or smaller? It gets bigger. So these are the small ones, and these are literally the big ones. And then, guys, moving from left to right across a period, where are the big ones? On the left or the right? They're on the right. Wait, did I say big ones or small ones? Oh, my bad. Big ones, sorry. Big ones are on the left. Small ones are on the right. So, guys, these are the biggies. And these are the smallies. But then, guys, the interesting bit. How do we know that this is true? What evidence of this do we have from the previous unit? PES spectra. right? Guys, now you have the understanding of effective nuclear charge, shielding. We drew the PES spectra where we saw that as the nucleus was getting stronger, these peaks are shifting to the left, which is representative of not only the fact that there's a tighter attraction, but also a smaller radius. Guys, we said that literally you can think of this as being the nucleus, and then the distance is actually the attraction, which is represented by the distance from that maximum is actually representative of size. And so as we move left to right, more protons in the nucleus, stronger effective nuclear charge pulls this thing together. Then as we go from top to bottom, we're adding layers to the onion and they get bigger. So is that okay? Yep. Anything there you need to talk about? Okay, so let me get rid of that mess if I can. Oh, good. And so, guys, then relative to that, we went on from there and we started talking about electronegativity and ionization energy, and we had a general principle that you may not remember, but it's helpful for me to come back to. Guys, which atoms are the strongest, the big ones or the small ones? Small. So small is strong. If you want to jot that down, this is sort of for me. This for me is the thing that I can always fall back on when I'm freaked out on a test or when I'm trying to think through the principles. The small atoms are the strong ones. So as you move down, they get bigger and weaker, and as you move left to right, they get smaller and stronger. So guys, what is getting stronger? And the answer is both electronegativity and ionization energy. And I'll define them down here. So guys, electronegativity is stealing power. Ionization energy, which is what PES is all about, is keeping power. But they are both a reflection of effective nuclear charge and shielding, which then means smaller is stronger. Well, we should write in the trends. So these are strong. Here, and we'll just do it for both of them. These are strong, and these are weak, and these are weak, and this applies to both lines, and these are strong. How you guys doing? So where are the strongest elements on the periodic table? Top right. But guys, why is it not helium? Why is that not the most electronegative, not the most electronegative element? Because it's a noble gas and it's all full up. But guys, what about its ionization energy? Does it have the highest ionization energy? And it actually does, because it's really hard to steal from. So guys, the idea here is that helium doesn't have a high it has no electronegativity because it's got nowhere to put electrons, but it does hang on to the electrons that it's got really, really well. So it's got a very high ionization energy and no electronegativity. Is that okay? You guys good on that? Okay, so guys, now we're done. We just did chapter, 7? Guys, we just did chapter 7. So is there anything there that you need to talk about? You okay? Okay, so guys, I'm gonna test the waters here for a second. I'm gonna throw you a question, and guys, what I want to do is I want to let you think about this for a minute, and then I'm gonna have you conference on this for a second, and then we're gonna talk about it as our transition into chapter 8. And guys, the question is this: don't say a word, just think about it. Let everybody process. On the periodic table, where are the most reactive elements? Don't say a word. On the periodic table, where are the most reactive elements? Think about it for a second, and be ready to also justify your answer. On the periodic table, where are the most reactive elements? Do you have an answer? Okay, so guys, share it with the person next to you. Come to consensus. you would never know that those were staples. These, however,
oh, that's so cool.
These are actually premium Optima staples. Oh yeah, they are. So here we go. Oh yeah, be careful.
Thank you very much.
Oh, you bet. I know, right? I love that they come in a tin. Okay, guys, so this conversation that we are about to have is going to be our transition into what we're doing today in chapter 8. So, guys, we're gonna label some bits. So I think you probably said that these most reactive elements are in one of the corners, top, bottom, left, right. But guys, what I'd like you to do then is literally vote with your fingers. Which corner are the most reactive elements? Show me fingers. We got votes on 3, 1. Don't be scared. Vote, girl. I was afraid you were going to use a finger, but not the one I wanted to see. It's like, oh shoot, she's voting for 1 and she's mad. You got 3, we got 3, we got 2. Man, guys, we are all over the place. So guys, what if I told you this? You can't answer this question on one hand. I set you up for failure. So, guys, let's talk about the deeper chemistry that you actually need to be able to think through in order to answer the question. So, guys, it goes like this. The question was, which elements on the periodic table are the most reactive? So let's back that up. How do elements react? What part of an element is involved in reacting? The electrons, right? But now, guys, we've got to remember this magic staircase that runs through the periodic table. What does this staircase separate? The metals from the non-metals. And so, guys, this is a very important distinction, which is going to be our entry point into chapter 8. So, guys, let's remind ourselves. The metals are big and fat and weak, so are they electron givers or electron takers? Givers. Non-metals? Takers. So now we can come to both answers. So guys, all the elements on this side of the periodic table are givers. And so their reactivity is based upon their ability to give. And so guys, which ones are better givers? Well, if small is strong, then big is going to be weak, which means they're going to be good givers. They're victims. Everybody steals electrons from them. And guys, that would therefore place them down here. So the big, fat, weak metals in the bottom left are the most reactive metals. But now we need to remind ourselves that the non-metals are not electron givers. What are they? They're electron takers. So where will the better takers be? Top right. Guys, those are therefore your most reactive portions of the periodic table. Top right, because those are the the stronger non-metals. And then, guys, bottom left, because those are the weakest metals. And so those are your two areas of reactivity. Does that make sense? Being careful, though, that we understand that this does not include the noble gases, because the noble gases are all full up and they don't take in electrons very well because they have nowhere to put them. So, guys, that's going to be our bridge into chapter 8. Anything there that you need to talk about? You really okay? That idea makes sense. Okay, so guys, this then is how we're going to approach chapter 8. Chapter 8 is all about bonding, this idea of reactivity, this idea of electrons moving between atoms in order to form compounds. But guys, what we're going to do today is we're first of all going to lay some groundwork, and we're going to talk about what bonding is. Then we are going to quickly review ionic, covalent, and metallic bonding. And then, guys, we're going to do a deep dive into ionic bonding, and we're going to check off some of the stuff in your W column, right? KWL, what's the W? Want to learn, because you didn't figure it out when you read it. So guys, we are going to talk today about all of the fine details about ionic bonding, and then when we come back on Wednesday, we're going to talk about covalent bonding. We're not going to talk anymore about metallic bonding, because you don't need to know much, and what we're going to do today is going to be it. So again, what is bonding? Overview of the three types, deep dive on ionic. You ready to go? Concur? All right, let me fire this up. So guys, if you need more information about the trends that we just went over, I do have slides on those. Help yourself. But we're not going to do that together because we just did it. All right, so guys, getting started. In order to talk about chemical bonding, we need to define what a chemical bond is. Ready? Go. Guys, in your notes, do your very best to define what a chemical bond is. If you were explaining it to your little brother, somebody young asks you, how does hydrogen and oxygen turn into water? And you have to explain to them this idea of atoms bonding together to make compounds. What do you explain? Okay, did you really dress up as Donald Trump? Why did you not come by? Do you have pictures? I'm sure somebody does. You guys there? Okay, so guys, what I'd like you to do is please read your definition of bonding to the person next to you and help them understand it. Then once the one person is explained, trade roles. Talk about it for a second. Guys, you got about another 10 seconds. You all there? Oh, yeah. I'll show you a picture. When you see it, you're going to go, that makes sense. All right, guys, join me. What I don't want is I don't want sentences. But guys, what I would like are words. So you've had the opportunity to share in both directions. Were there words that you and your table mate both used? Electrons. Okay? So we know that bonding has to do with electrons. Guys, other words that you and your group mate also, you both used. Say it again. Sharing. Okay? Anything else? No other shared terms? Okay, so what about this? What about important terms? Because guys, these two terms together do not get us there. What are other important things we need to think about when we're thinking about bonding? Charges. Good. Say octets. Great. That's maybe a part of the answer to why. What else? You realize you're missing the very most important word, right? Yes. In the dictionary under redundant, it says see redundant. No? Say it again. Okay. Guys, fundamentally, what do bonds do to atoms? Stick them together. We call that attraction. So, guys, how did you define bond without using some sort of word that says atoms are attracted to each other? Don't be scared. Never be scared. Actually, sometimes be scared, but not now. All right. And then, guys, I heard an important word, Chase. You and Santiago were chatting, and I'd like to bring it out because we're going to use a different term. I heard you say electrostatic. Yeah. Which was awesome, but not quite correct. So, guys, other terms that you would like to add to the list? You're good? Okay, so here's what we know. We know this has to do with electrons. At least Josh and I knew this had to do with attraction, but he was afraid to say it. I'm a little more bold. So we have this idea that we've got charges that are creating some sort of electrostatic attraction, moving towards fulfilling octets. But guys, understand it doesn't have to fulfill the octet rule, but it is moving towards stability, right? Because we can talk about stability, we can talk about spontaneity, we can talk about releasing energy. And guys, you're comfortable with this, right? Anytime a bond forms, energy is released. And we can say every time a bond is formed, energy is released. How do we know? Because if it wasn't, they wouldn't bond, right? But guys, understand energy doesn't have to be heat. What evidence do we have that that energy doesn't have to be in the form of heat? The heat of solution lab, y'all. We saw that some of your solution processes were endothermic, some of them were exothermic. So these formings of interactions, whether they're bonds or intermolecular forces, doesn't have to necessarily, the heat exchange, the energy exchange doesn't have to be heat. It can also be entropy, but that's where Gibbs free energy comes into this. So guys, all great ideas. Let me bring this together into one big nugget. And guys, this is going to be our functional definition for a chemical bond. It is a force of attraction between two atoms which occurs whenever two atoms or ions are strongly attracted coulombically to one another. So wait, we never mentioned electrons. We'll talk about why. So guys, let's talk about the important bits that we need to have our heads wrapped around. First of all, attraction's critical, right? Attraction is what this is all about. Atoms sticking together, so it's got to be about attraction. But guys, we also have to understand that these things exist one atom to another. Yeah, we can have complex molecules where there are lots of different atoms bonded together, but we study them one atom bonded to another atom, even if that atom is then bonded to other atoms as well. So it's one or two at a time, or it's two at a time. Then guys, this can be atoms or ions. That's why we're not talking about electrons. Because, guys, electrons work when we're talking about covalent bonds, the sharing of electrons. But when we talk about ionic bonds, then, guys, it's got to be about the ions attracting each other. And then at that point, it's not about electrons. There is an exchange of electrons that creates the ions, but it's not the electrons themselves that are involved in the attraction. And so, guys, we're not going to talk about electrons because that doesn't include ionic bonding. Then, guys, this word is critical. Strongly. Why do we have to say strongly? Because we can also have attractions between atoms and ions that are weak, and those are called intermolecular forces. Guys, the attractions work exactly the same, they're just not as strong. And so we don't define strong other than to say that there are other interactions that are weak, and those are called intermolecular forces. And then, guys, the last thing we need to do is talk about coulombically. And, guys, a coulombic force is a force based upon charge. So a coulombic force is a force based upon charge. Understand, it doesn't have to just be attraction. Protons repel each other in the nucleus, and that is also a coulombic force. But, guys, coulombic forces are simply forces that exist between particles based upon their charge. Opposite charges attract, and then similar charges repel. Anything there? You guys good? We okay to go? Okay. So, guys, with that said, then what we're going to do, and you write down what you feel you need to, but this is all review. Because we are going to review ionic, covalent, and metallic bonding. And then, guys, at that point, we're going to do a deep dive into ionic bonding, talk about lattice formation, and then we're going to be done for the day. So, guys, take notes right now judiciously, because this is all review. But here we go, and let's talk about ionic bonds. So, guys, let's just brain dump for a minute. So here we go. So we've got metals, we've got nonmetals. What pairing of those creates ionic bonds? A metal to a nonmetal. So metals big and fat and weak, and they give away electrons, right? Nonmetals small and strong, they take in the electrons. So when a metal loses an electron, what does its charge become? Positive. When the nonmetal takes in the electron, its charge becomes negative. Positives and negatives attract. You now understand that those are called coulombic forces, and they attract each other, and they form ionic bonds, which then cluster together in big old groups, and we end up with these, which we call salts. Right? Remember, guys, salt is not just NaCl. Salt is any positive and negative ion bonded together in a lattice. This happens to be sodium chloride, sodium and chlorine. But, guys, those form salts. So, questions or things you need to talk about with ionic bonding? Do you need to write any of this down? You okay? So, guys, here's what we know. It's a coulombic force that exists between ions. It's formed by a metal and a nonmetal. And when these form, you've got a stealing of an electron, which creates opposing charges and attraction. And then those all clump together in a lattice. So, guys, let me pause. Let me let you write anything down. You may want to include the idea that those lattices are then called salts. But there you go. Give you a minute to jot down the stuff you find important. Yeah, so lattice formation. So it goes like this. So the idea, holy smokes. So the idea is that we've got a sodium and a chlorine, right? And so what happens is the chlorine steals an electron from the sodium. This becomes negative, this becomes positive. So now we have ions, positive and negative ions. But these don't just come together like this. It's not like one sodium finds one chlorine and goes, hey, let's ionically bond. What happens is groups of positives and groups of negatives get together where you've got, for example, one sodium attracted to 6 negative chlorines, and they create these complex structures that we call lattices. Okay, it used to be, and this is deeper in chapter 8, it used to be that you had to know the names of all of these different lattice structures. That's gone now. So guys, if you dig into chapter 8 and you see the stuff in there about face-centered cubic and bicubic and rhombic and all those other lattice structures, you don't need to know that anymore. But you do need to know there's a mass attraction where multiple sodiums are surrounded by multiple chlorines and so on. Okay, so guys, are you good on that? Any questions on ionic bonding? Okay, so guys, this is what we're going to come back to in a couple minutes. Because there's a little bit more to this than meets the eye. You need to know about some of the energies that are involved in this lattice formation, and we're going to talk more about that in a minute. But before we do, we're going to move on and we're going to talk about covalent bonding. We're just doing an overview of each of the different bond types. So, guys, again, a similar question as the first. So we've got metals, we've got non-metals. We've already said a metal and a non-metal makes an ionic bond. So, guys, what atom pairing leads to covalent bonding? Two non-metals. So as two non-metals come together, they start to fight and attract each other's electrons. That's electronegativity. And they start tugging on each other's valence electrons. But because they're both non-metals, both of them are strong, they pull, neither one wins, and as a result, they end up sharing, and we call that sharing covalent bonding. Is that okay? Okay. So guys, what about this then do we need to talk about? Oh shoot. Sorry. So we've got covalent bonds. So it results from the sharing of electrons. It's formed by two nonmetals. And then guys, I know you're going to read this and you're going to go, okay, process of hybridization or process of formation, they're sharing. But guys, you're going to find out in this unit that is preceded by something called hybridization. It's not something you learned last year. My suspicion is, actually, no, it's in Chapter 9. And Chapter 9 is going to be a part of this unit as well. We'll talk about it later. But understand, guys, when covalent bonds form, something magic, it is actually kind of magic, something really interesting happens first called hybridization, and we're going to talk about that more later. You guys good? Overview of ionic and covalent. Anything there? Okay. So, guys, let's wrap this up then. So we've looked, oh, please, Kate. Yeah, and so yes. And so when we get deeper into covalent bonding, and especially when we get into molecular structures, we're going to talk about the polarity of the bonds, which is just unequal sharing. But you're right, that's a related topic. But we're not going to so much get into it in Chapter 8 as we will in Chapter 9, which is a part of this unit, because Chapter 9 is about molecular structures. And once we start thinking about molecules, we can then talk about symmetry and lopsidedness and all that polarity stuff. So yeah, it's coming, but not for a couple days. Yeah. You guys good? Okay, so guys, look at what we've done. Metal, non-metal, ionic. Two non-metals, covalent. What's left? Metal to metal. Metallic bonding. And so guys, this is the last one that we need to talk about. Metallic bonding is this interesting idea that you get these metal nuclei together. They're all big and they're all fat and they're all weak and they're just like bleh, just throwing electrons everywhere. Electrons start to just flow throughout the substance. And guys, we end up with this picture, which we call a sea of electrons, which is actually a term that you can use on the AP test. It is an accepted convention. But the idea here is what we're really talking about are what are called delocalized bonds. These are bonds without location. As these big, fat, weak metal nuclei are just letting electrons wander all over the place. And those metal nuclei are positive. They're floating around in a sea of electrons. And the nuclei are all loosely attracted to that sea of electrons. And as a result, you have this weird metallic bonding going on. So guys, anything there you need to talk about? Is that coming back to you? Remember, this then explains all of the interesting properties that we know to be true of metals. So if we have a metal like this piece of aluminum, guys, we know that aluminum conducts electricity. Why do metals conduct electricity? Because the sea of electrons, literally, guys, please don't do this, but if you were to shove this into an outlet, again, let's don't, but guys, all electricity is a flow of electrons. So if you were to stick a metal into a place where there's electrons in an outlet, literally, if you plug this thing into an outlet, electrons move into one side of the metal. They just cause this sea to drift in this direction. The pressure that they do that with is called voltage. We'll talk more in chapter 20. And then electrons come out the other side. And so literally, guys, all an electrical current is a pressure of electrons pushing electrons in one side, moving the sea out the other side. And that's why metals conduct. That's also why electrons are shiny. You understand this? That sea is very, very flat. If you've ever been up in a mountain lake and it's dead still and the lake looks like a mirror and you can see the mountains reflected off the surface of the lake because the lake is really flat and reflective. Guys, that's why metals are shiny. This sea of electrons is really, really flat, and when light hits it, it's reflected. It literally bounces off. It just skips off the surface of the electron sea. That's also why metals are malleable. Because, guys, when you bend a metal, literally all you're doing is smearing the sea of electrons. So metals are bendy. So all of those things are true. By the way, how do we then make metals that are not bendy? Yeah, exactly. They're called alloys. Guys, what they do, why are the legs of your table not bendy? And the reason is this. What they do is for the legs of your chairs, guys, most of these metal ions in steel are iron. But guys, iron is actually on its own surprisingly bendy if it's just iron atoms. What they do is they create alloys. And when they create alloys, what they do is they put other kinds of metal atoms. In this case, a lot of times they use molybdenum. And the molybdenum actually creates different polarities within that lattice structure, and it causes it to become rigid as we take different types of metal atoms and stick them together. Yeah? Yeah. So interesting, right? So absolutely. Yeah, Isaac, it's a really interesting point. Wouldn't it be stronger if it's non-metals, right? But then we get covalent bonding. And so a great example is this, which is diamond, right? The strongest substance on Earth. And that's what we've got is actually a lattice made of covalent bonds. The problem is that we lose some of the other properties of metals that we want. Like this doesn't conduct electricity. Diamonds insulate very, very well. They're also very brittle, right? This doesn't bend. And actually another example is graphite. Again, all covalent bonds, but it's very brittle. So you're right that we can make stronger structures by using covalent bonds, but then we lose the other metallic properties that we need, and so metals have a place as well. Yeah, but if you're just looking straight for strength, definitely covalent bonds are the way to go. That's why they build bike frames out of carbon. Like my bike has a carbon, it's a carbon synthetic bike frame, and it's super light and really strong. Stronger than metal because of the covalent bonds. So absolutely. You guys good on metallic bonding? Y'all set? All right, so guys, we're going to spend the next 20 minutes and we're going to do a deeper dive into ionic bonding. In order to do this, guys, you need your books now open to page, wait for it. Keep waiting. There we go, 293. All right, so guys, my strong advice to you would be don't try to write any of this down, just enjoy the ride. What we're going to do now is we're going to do a deeper dive into ionic bonding. But guys, in order to do this, we are going to consider our good friends sodium and chlorine forming table salt, which we've already talked about looks like this. So guys, thinking about the process of formation, how does this go? So let's think about what's going to happen. So here we've got sodium, here we've got chlorine. Sodium's got 1 valence electron. Remember, that's given by the group, right? Sodium's got 1, chlorine's got 7. Now guys, which one is stronger, the sodium or the chlorine? Chlorine, right? As we move to the right, they get smaller and they get stronger. So chlorine is a non-metal, will have a higher electronegativity than sodium. So guys, what is chlorine going to do to sodium? Steal its electrons. So right, I animated it. Oh yeah. Come on. I know, it was some of my better work. There was a little glitch though. Did you see it? I didn't quite know what to do, but that's the best I could do. And so we're just going to run with it as a success. Okay, so now guys, we've got sodium and we've got chlorine ions represented on the screen. But now, guys, we need to talk about energies. What you just saw, you already knew. You know that ionic bonding is the process of stealing, that the strong non-metal chlorine steals from the big, fat, weak metal sodium. That makes a chloride, -1 ion, a sodium, +1 ion, negatives and positives attract, zip, bang, pow, ionic bonding, right? Now, guys, let's do this. Let's talk about the energies that are involved in this. So guys, focus your attention on sodium. And I know that you're just easing into this, but guys, these are important questions you should be able to answer. Guys, when we hit the space bar again and let this go, what is going to happen to that electron on sodium? What's going to happen to this electron? It's going to go away, right? Where does it go? It goes to chlorine. Is that process endo or exothermic? Let's say this again. Guys, you seem confused, which is terrifying to me. Focus, kiddos. So guys, sodium is going to lose its electron. You know, and eventually it's going to go to chlorine. But guys, just looking at sodium, it's going to lose its electron. Is that process endo or exothermic? Endothermic. How much energy does it take to do this? Ionization energy, electron binding energy, everything you learned in chapter 6, which you don't have the luxury of forgetting. So guys, how much energy does it take to make this happen? Guys, what we're talking about is this. We're talking about all of our energy levels. And we're going to take this electron and we're going to kick it up to which energy level? Infinity. And at that point, bye-bye, and it's gone. Sodium is losing its electron, and the amount of energy that it takes for that to happen is ionization energy or electron binding energy. But guys, in either case, energy has to go in to make this happen. That is endothermic. Does that make sense? If it doesn't, please ask questions. Great question. And I'm going to show you a video in just a minute. Where does the energy come from? But what about this? It's endothermic, so is it spontaneous? No, right? So sodium is not just going to be hanging out, chilling, going, hey, yo, I'm giving away electrons, right? Because it's endothermic, and as a result, it's not spontaneous. So we need an outside energy source to make it happen, and we'll talk more about that in a minute. You guys okay? Okay, now guys, this. Where does this electron then go? Does it just go away? No, where does it go? It goes into chlorine. So guys, let's pick up the story from here. And here's our electron, and that electron goes in. And as that electron falls into the chlorine atom, is that endo or exothermic? That is exothermic. And many times, guys, how does that energy come out? In the form of light, huh? See how this all ties together? We couldn't have this conversation without having done chapter 6. So this is exothermic, and that energy comes out as heat and light, but that is always exothermic as the electron is falling into the chloride atom. Is that okay? Okay, so guys, let's do this again then. Do you need to pause there at all? Okay, so guys, let's come back and do this again. And that electron moves over, and so the electron was released by the sodium. That's an endothermic process, and the electron was captured by the chlorine, and that was an exothermic process. You guys okay with all of that? Does that work? Okay. So guys, now what we're going to do is this. We understand that this is endo and this is exo, but now we're going to start talking, and Maddie, this is where we're going to get to the answer to your question. We're going to start looking at the whole picture. And guys, what we need to do is understand that this entire process is very, 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 very exothermic. So we understand that we've got two competing processes. We understand that this is endothermic. We understand that the capture of that electron is exothermic. But guys, the overall process is very exothermic. And if you don't believe me, let me show you this process.
This is one of my favorite experiments. Supposing you want some fresh salt. None of that stale old store-bought stuff. You want the fresh stuff. You got to make it yourself. Well, how are you going to do that? Salt is sodium.
Okay, so here's what we've got. Guys, this is sodium metal. It was sodium metal.
This is one of my favorite experiments. Supposing you want some fresh salt. None of that stale old store-bought stuff. You want the fresh stuff. You got to make it yourself. Well, how are you going to do that? Salt?
Okay, here we go. So guys, this is sodium metal. Why is it stored in mineral oil? Do you remember? What's that? It is not oxygen, water. Guys, sodium has, all of the group 1 metals have these really unique abilities to take water and rip water apart. And when they do, they actually make sodium hydroxide. I don't know if you can picture this or not. But what happens is the sodium metal, I'm going to write water as HOH. And what happens is it makes sodium hydroxide, but then the hydrogen gets kicked out. And then it catches on fire, and then it blows up. So guys, we have to store sodium in mineral oil, because if we don't, the humidity in the air can cause it to spontaneously burst into flames. That's bad. Then guys, this is chlorine gas. You may remember last year when we talked about this. This is mustard gas. You breathe this in, and it reacts with the water in your lungs, and it turns into hydrochloric acid, and you literally digest your own lungs that's mustard gas poisoning. That's how we killed a lot of people in World War I. So, guys, we've got sodium, we've got chlorine. But what we're going to do now is we're going to let these things react together. Yeah. Yeah. Exactly. Exactly. Although a spark isn't quite enough, so we're going to go with blowtorch. But there has to be an external addition of energy to get this started.
Sodium chloride. Sodium is a metal that explodes on contact with water, and chlorine is a deadly poison gas. They actually used it in World War I as a poison gas.
Yeah, so there's your activation energy. So guys, what we've got is we've got sodium metal in this large crucible. And then over here we've got the cylinder of chlorine gas. Blowing chlorine gas, you can see the tube turns to metal because it would melt. And they're blowing chlorine gas across the sodium and then adding, Maddie, as you said, some energy to get this started. But guys, look for evidence of this reaction being exothermic.
If you take a bowl full of molten sodium and you blow...
See the exothermic? Guys, all of the light and heat that is being given off, you'll notice the blowtorch is gone. This thing is now going on its own. And guys, as it does, all this heat and light that is coming off of this is the energy, the exothermic energy that's being released by the process. You'll notice too, though, guys, there's a lot of smoke. What is the smoke? Table salt. The smoke of this reaction is literally pure table salt. So this guy thought it would be cute to hang a fishing net full of popcorn above the reaction to salt the popcorn. Some of you may remember how this turns out.
And gas into it, you get a fire, and the smoke coming off of that is pure salt. So we hung some popcorn over it. Salt popcorn with nice fresh salt.
What's going to happen? The net melts.
And it worked great. We got some good shots we used in the magazine. Then turns out the net started melting, and it actually dropped the popcorn into the molten sodium. Sodium exploded, and you got
This is why we wear PPE.
popcorn and sodium flying everywhere. That's really not such a bad thing. It tells you that science doesn't always go the way it's supposed to. It tells you why it's important to wear a face shield and have all
You guys seeing all that exothermic? Oh yeah, exothermic.
the right safety equipment. And it made some really good shots that we could use also.
All right. So guys, here's what we now know. We know that this overall process is exothermic. So the question becomes this. Which one requires more energy? Remember, this is endothermic and this is exothermic. Sodium losing an electron is endothermic. Chlorine capturing that electron is exothermic. Guys, here's the question. Which one, the one on the left or the one on the right, which one involves more energy? The one on the right. How do we know? Because the whole reaction is exothermic. Guys, these are sort of the logical things you've got to be able to think through. The idea is this is always endothermic, this is always exothermic, and if the whole stinking thing is very exothermic, doesn't it make sense that the thing on the right has got to involve more energy? Yes? Turns out the answer is no. Guys, it goes like this. Here's the however, and I don't think you need to write this down, but just follow along. Guys, it turns out that we know this, the losing of electrons is endothermic, always. The gaining of electrons is always exothermic, right? But here's the thing, guys. Losing electrons, what happens to sodium? This is generally, and in the case of table salt, definitely, this requires more energy to go in to lose that electron than the energy that comes out when the chlorine captures that electron. So guys, the endothermic losing of electrons is more energetic than the exothermic capturing of electrons. And now we have a problem. Do you see the problem? Guys, what we now know is that this involves more energy than this, but we know that the entire process, we saw the fire, we saw the net, we saw the explosion. Guys, we know that the overall process is very exothermic, but it takes more energy to snitch an electron off of this than this releases when it captures it. So guys, what's going on? And the answer is, this isn't the complete story. Guys, if the formation of table salt simply involved this, if the formation of table salt simply involved an electron going from the sodium to the chlorine, then this would be endothermic. Say that again. If that was the end of the story, if we added energy to the sodium and the sodium goes, woohoo, and it loses an electron, and then the chlorine goes, hey, I got you, and it captures it, because this would be endothermic. It takes more energy into this than comes out of that. Yeah? It's not. What is going on? Guys, what is happening that makes the whole process exothermic? And right now I ask sort of rhetorically. But guys, let's see if we can figure this out. So if all it was sodium losing an electron and chlorine picking the electron up, this would be endothermic. But guys, that's not all it takes to get over there. What does it take to get over there? The formation of the lattice. And guys, that's where all the energy is coming from. So the energy that you saw that was lighting up that video had very little to do with sodium losing and chlorine gaining electrons. All the energy that you saw released were all of these ions coming together and going bump and turning into a lattice. Guys, these lattices are very, very stable. And because they're very stable, their formation loses a pant load of energy. And so, guys, that is the answer to why this entire process is exothermic. Why is the entire process exothermic? And the answer is lattice formation. The formation of this lattice, guys, is where all the energy comes from in this process. So I don't know if you need to write this down or not, but the idea is this. As the attraction between the positive and negative ions draws this thing closer together, energy is released as we form this array or this lattice. And guys, that is why these formations are exothermic. It's not because of the exchange of electron, it's because of the formation of the lattice. These things are crazy stable, and therefore a lot of energy comes out when they form. Yes. Yes, they have weak lattice energies, and what you actually see is that a lot of the energy that was driving that process was actually entropy. Yeah, that's exactly right. You got it. So, guys, you settled in on this idea. This is the big idea with salt formations, ionic bonding. The energy of ionic bonding is not the energy of the exchange of the electrons. It's the energy of lattice formation that gives off lots and lots and lots of energy as that lattice forms. Yeah. And that's exactly where we're headed in 2 seconds. Yeah, and that's actually one of the things you need to know for the AP test is what... So yes, stronger lattices release more energy. The question you have to be able to answer is what makes lattices stronger? And we're going to talk in just a second. So guys, let me share this with you then. Do you see it? Guys, this energy diagram, and I told you we're going to be doing energy diagrams. Guys, this energy diagram explains what we just talked about. So let me do this for you. Guys, this starts right here. That's where it begins. We've got the sodium that's in the crucible, and we've got the chlorine gas that is in the canister. But now, guys, let's look at the steps. What does step number 1 represent? What's happening to the sodium? It's boiling. Guys, imagine trying to boil sodium. So, guys, this first step is sodium from a solid into sodium as a gas. This is the entire energy picture of the video that you saw. So the first thing we've got to do is break the sodium lattice apart and turn the sodium into gas atoms. Now, guys, what happens in step number 2? The chlorine is breaking apart. The Cl2 is breaking into individual chlorines. Now, guys, what's going on in step number 3? What happened to the sodium? It lost its electron. Guys, remember we said that energy has to go in. That's this electron jumping up to energy level infinity. So guys, energy has to go in order to strip the electron off of the sodium. Now guys, where does this electron go? It goes to the chlorine. And when it goes to the chlorine turns into negative chloride ion, and that's exothermic, right? But guys, remember what we said. the amount of energy needed to strip the electron off of sodium is greater than the amount of energy that's released when chlorine captures the electron. So guys, if this were the end of the story, this process would be endothermic. But then look at what happens. Woohoo! Guys, what is all of that energy? That's the formation of the lattice. And guys, all of the energy that is released as the lattice forms finally gets us down here to the table salt. And the difference between where we started and where we ended up, this goes down, indicating that energy is released. Do you see the complete picture? So guys, the question then becomes this, and Maddie, this is where you took us. Guys, what is it that determines, let me do it this way. What is it that determines how much this energy is going to be? And guys, this is what is called lattice energy. And so on the test, you have got to be able to intelligently talk about what is it that determines the lattice energy for a salt. So guys, do this with me. Turn your attention to page 292. Actually, no. Turn your attention to page 293. And guys, on page 293, you see this table. Your colors are a little different than mine, but you see this table. So guys, allow your eye to scan through this table. First of all, this. You should have a serious problem with these numbers. Fundamentally, they're all wrong. Why? They should be negative, right? Because we understand that negative energy means exothermic. But guys, all of these numbers are positive. Do you understand that they should be negative? Lattice energy is exothermic. So why are they positive? Guys, go over to page 292, and you see where it says lattice energy in bold? Read the definition. Lattice energy which, do you see why they're all positive? Why are they all positive? The energy required to break the lattice. So guys, lattice energy, which is the energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. So guys, the definition of lattice energy is the amount of energy that it takes to break the lattice. But if we know the amount of energy it takes to break the lattice, how much energy is released when the lattice forms? The same amount. That's the first law of thermodynamics. So guys, the energy that it takes to break it is the same as the amount of energy that's released when it forms. So guys, they just make it positive instead of negative, but the amounts are the same. So now guys, this question, and this is how we're going to wrap up the day. Guys, what are the factors that influence the strength of the lattice? Guys, tear this table apart. Look at the trends in lattice energy. What are the things that determine the strength of the lattice? I'll give you a couple minutes to think about it. Feel free to chat with somebody if you'd like. Guys, what determines the strength of the lattice? So guys, let me give you a little bit of a head start if you're stuck. Maybe this helps. These examples are clustered into 4 groups. Give you another second now that you see that to think about it. Can we talk? Okay, so guys, looking at these groups, you'll notice that in each one of the groups we have a control. We understand, guys, that if we're trying to establish relationships between different things, we need to have controls. So in the first group, lithium is the control, then sodium, then potassium, then cesium. Then, guys, you'll notice that from there, the nonmetals are all halogens. Chlorine, bromine, iodine, and others. So then, guys, look at the way these are organized. Fluorine, chlorine, iodine. Fluorine, chlorine, iodine. Fluorine, chlorine, bromine, iodine. Fluorine, chlorine, bromine, iodine. So how are the nonmetals related to the periodic table? Top to bottom. So guys, look at what happens. As we move down to halogens, does the lattice become weaker or stronger? Weaker. Why would that be true? Why would moving down the halogens group make the lattice weaker? What do we know about what happens as we move down? Does have a kind of ionization energy, but not directly. And weaker, but not quite. Because remember, guys, weaker and stronger is about stealing. And the stealing has already happened. They're all strong enough to steal. So it's not directly related to ionization energy or electronegativity. Go ahead. Closer, getting closer. It is not quite about core electrons. They're bigger. Guys, literally, they're getting bigger. So this is sodium, right? But this is sodium chloride. What if we went down and did sodium bromide? How would this change? The green guy would physically be larger. And so, guys, the larger these ions are, the more spread out they are, the more distance between them, and the weaker their attractions. Does that make sense? So ionic, and you need this in your notes, guys, ionic size is one predictor of lattice strength. Again, ionic size is one predictor of lattice strength. What's the relationship? Is it inverse or direct? Inverse or direct? The bigger the ion, the weaker the lattice. Bigger ions, weaker lattice, that's indirect. As one goes up, the other goes down. The bigger the radius, the weaker the lattice. But guys, that is not the major predictor. Check this out. All these numbers are in the order of hundreds. But now, guys, look at these numbers. Moving over to the right, you'll notice that these lattice energies are hundreds, tens of times bigger. So, guys, the question becomes, what's going on? Well, notice still, now we're controlling for the negative ion. And as we go down the groups, they still get bigger and therefore weaker. So we go magnesium down to strontium. As we go down, the strontium is bigger than magnesium. That makes it weaker. As we go down, magnesium, calcium, strontium, those get bigger, it gets weaker. But guys, what is happening here that makes all of these lattices stronger than anything we see on the left? How are the examples on the right different? Yeah. And therefore, not quite. Guys, how would these examples be different? Charge. So, guys, the idea is this. All of these are +1, all of these are -1. Over here, we have +2 and -1. Here we have +2 and -2. Here we have +3 and -3. So guys, charge is also a predictor of lattice strength. Now let me ask you this. Which is the major predictor? Does lattice strength depend more on charge or more on size? Charge. Look at how big these numbers are. So guys, the strength of the lattice is predominantly dependent upon its charge, the charge of the ions that make it up, which makes sense, right? The more positive and negative things are, the more they stick together. So the major predictor is charge, the secondary predictor is size. So guys, with those things floating around in our brains, that's all contained in your notes. You can look these up later. And guys, here's your homework. So guys, this then is where we're going to stop. And we are going to take a break. And when we get back, we're going to dig right into lab.